Hi, good afternoon, everyone. Thanks very much for coming. I hope you're all having a great time at TechEd this week. So my name is Val Fontama. I'm a senior product manager for big data and predictive analytics in STB marketing. And I'm very proud and pleased to present this session today with my partner in crime, Saptak Sen. Saptak, do you want to introduce yourself?
Sure. Hi, my name is Saptak Sen. I'm a senior product manager as well in the Azure Data Platform team. For last 9 years, my focus has been around distributed computing. He's the expert on data mining part of it, so I'm going to cover the last part of it, which is around how you can do data mining on a big data platform.
All right, thanks very much, Saptak. Okay, we have a very busy agenda today. There's a lot of goodness we want to share with you, so let's get cracking. We have 5 key things we want to cover in today's agenda. First, I want to start with an introduction to predictive analytics. For those who've done it before, please bear with us. For those who haven't, I think it's a good place to start to ramp everyone up. Second, I want to show you what tools Microsoft offers for predictive analytics. Third, to make it real, we will show you how we are actually applying some of these tools to solve real business problems at Microsoft. And of course, no TechEd session is complete without demos. So we have some goodness waiting for you. But we want to wrap up as well with pitfalls you should avoid when doing predictive analytics. So before I continue, just a quick show of hands. How many people in the room have done predictive analytics before? That's great. In fact, it's more than I thought. So you're definitely in the right place. Okay. So most of the analysts are really hot on this area, right? Based on the demand they're seeing from the market. And Gartner has made their own forecast about where this market is heading. So just think for a moment. What percentage of analytical applications do you think will have predictive capabilities built in by next year? Is it 10%, 30%, 50%, or 67.8%? Take a second to think about it. I think we have a giveaway there. Not quite. If you thought it's B, 30%, you are definitely right. Gartner predicts by next year alone, up to 30% of analytical applications will actually have predictive capabilities built in. Our goal today is to have 100% of you in the room start building your own predictive analytic capabilities by next year. So why are we seeing so much interest in this area? Predictive analytics in itself is not new, right? It's been around for longer than myself. But in our view, there are 4 reasons behind this new interest in the area. Number 1, data explosion, right? You all know it, you all see it. But with the large data sets we're seeing, it's now impractical to get insights by just analyzing it manually. You can do all fancy charts, you can build all the fancy charts you want, you can slice and dice however you want. But if you analyze these large data sets just in 2 or 3 dimensions, it's very hard to find the insights. So you really need machine learning to be your able assistance there, because given the volume of data we're seeing, to get good insights is almost like finding a needle in the haystack. But the upside for all of us is that more data is a good thing, because everything being equal, the more data you have, the more accurate will be your predictive models, right? That's just the law of statistics. Because the more data you have, the smaller your margin of error. The second reason behind this interest in predictive analytics is we have much more computing power now than ever before. And it's much cheaper than it's ever been. You know the story. Compute power has increased exponentially in the last few decades, and the cost has reduced steadily. Just as an example, back in the mid-90s, when I did my PhD, to do data mining, I started off, we're renting time on supercomputers, right? But then the costs racked up very quickly. And so we got to a point where the university had to buy a dedicated DEC alpha machine just for me to run my algorithms on. That's too expensive, right? And not every organization can afford to buy those high-end machines just for this. But today, however, we're in a very different place because most of the servers we run now under our desks are far more powerful than the large supercomputers we had in the mid-90s. And then if you move into the cloud, for instance, you get even more scale and compute power than ever before, but only at a fraction of the price. The third reason behind this thing is I think we're seeing much more awareness in the market. Customers are much more aware of the value of predictive analytics now. You know, back in the 90s, frankly, data mining and predictive analytics was very, very niche. But today, thanks to companies, the Web 2.0 companies like Facebook, LinkedIn, and Amazon, I think more of, the average consumer now sees the value of these machine learning capabilities. But the last reason we believe there's so much interest in this area is that finally, we have the right set of technologies to really run machine learning at scale, right? Starting with the cloud. With the cloud, we now have elastic scale. You can go in and run a large data and compute-intensive job using the full scale of Windows Azure without breaking the bank, right? It'll only cost you a couple of dollars. You don't have to buy supercomputers for it. Second, we have technologies like Hadoop that allow us to store and manage large scales of data, literally petabytes of data at low cost. Then there's streaming engines like Stream Insight, which you can use to do data mining in real time. So put together, these three technologies really enable you now to build and run predictive analytics algorithms at very, very large scale and at affordable prices. But before I go any further, I thought it was important to just share how we think about predictive analytics. Because I've seen a lot of definitions out there, and my personal view is they're either too cryptic or just, frankly, gobbledygook. It's not rocket science, guys, sorry. Predictive analytics, in our view, really describes the class of analysis you do, not just using OLAP cubes, but the analysis you do with mathematical tools from either statistics, machine learning, or data mining. And these techniques typically find hidden patterns in the data that leads to direct competitive edge, right? And I think that's one of the reasons you're seeing a lot of interest in this area, because these algorithms typically, when they find good insights, it's usually not common insights. It's not intuitive, right? And it's the kind of thing you can actually use to outperform your competitors. And there are three classes of predictive analytics we see in the market. The first is diagnostic analysis. And here you're simply using these tools to answer the question, what happened and why, right? So we can use it to build customer segmentation models, to understand customer behavior. Why are our customers responding in the way they are, right? And there's a whole range of tools from statistics and machine learning you can do, like clustering techniques or classification. The second class is purely predictive analysis, where you're doing things like forecasting or trying to predict the most likely outcome in the future using historical data, right? And this is typically used for the areas of forecasting. If you're trying to do weather forecasting or even demand forecasting, you basically use historical data to predict forward. And again, machine learning, statistics, and data mining offer some pretty powerful tools, things like neural networks, regression analysis, and all of that, genetic algorithms for building predictive models. And then the third class, which is not widely used, is the area of prescriptive analysis. It's a type of analysis you will do to understand what's my best next action, right? Typical example is, say you have $5,000 to invest in your 401k plan. How should you spend that money? Do you buy individual stocks? Do you buy into mutual funds or bonds? Or in fact, all of the above. And if so, how do you invest the money? How much bond do you buy versus mutual fund or stocks? And that's a classic optimization problem, right? You also see this in other domains like network optimization, traffic optimization, scheduling, for instance. And there's a whole range of well-tested algorithms from statistics, machine learning, and data mining, again, to help. Tools like Monte Carlo simulation, game theory, linear or nonlinear programming. They were designed for this class of problems. So predictive analytics, as I said, is not new. It's actually being applied in a wide range of industries to solve very specific problems. We have just a subset of those problems out on the slide here. I wouldn't go through every single one. Let's just talk about two in the interest of time. The first one is churn analysis. And this is very, very widely used in the telecommunications space. Because of the intense competition, especially for cell phone operators, what they're seeing is very high attrition of their customers. As soon as you run out of your contract, you want to get the best deal. So most people leave after their contracts expire. And so most cell phone operators use predictive analytics to predict which customers are most likely to defect, right? And if you know that information beforehand, you can then target those customers with the right offers to retain them. So predictive analytics is widely used to make those predictions. The second one is fraud detection. Again, fraud detection in itself is not new. I built fraud detection models for banks 10 years ago. So what's new about this? What's new with fraud detection, and we're seeing a lot of interest from both banks and healthcare organizations, is that first, we have a lot more data than ever before, and as I said, now you can build more accurate models. And second, we now have the right technologies in place to be able to make those predictions in real time. And for those industries, the correct prediction of fraud is worth literally billions of dollars, right? Today, those of you in financial services will realize that the models we use are not very accurate, which is why, every time you travel out of your home state and swipe a card, maybe in Amsterdam, your bank blocks it thinking it's a fraudulent transaction. So to compensate for the inaccuracy of their models, most banks today do the processing in batch mode after the fact. But, if you catch fraud after the fact, it's too late. By then, you're already liable for the fraud. You have to pay the customer. And now you're in loss mitigation mode. So banks and healthcare organizations are very, very interested in these new big data technologies, specifically in predictive analysis, to really improve the accuracy of their fraud detection models. So that said, how do you go about building a predictive model? There are many different tools out there, but it really boils down to a 5-step process. And it starts and ends with the business problem, right? Before you start building your first predictive model, if you haven't done so, it's critical to be very clear what business problem you're trying to solve. Without that, you could spend so much time, burn compute cycles, and basically end up with insights that's not useful to anyone. If it's not actionable, there's no point doing it. So once you define the business problem you're trying to solve and the parameters, how it will be used, the next step is data collection and preparation. This is absolutely critical because the old adage about modeling is still true here. Garbage in, garbage out. And typically with predictive analysis, you're pulling data from several sources. Some will be internal, others will be external. You have to invest the time to truly understand the data. Deal with missing variables. Try and understand which variables are what's the word? Understand covariance between variables. Which variables are highly correlated with each other? What's in your continuous variables? What do they actually mean? Right? It's not obvious, because if you say missing data, for instance, what do I do with missing data? Do I simply throw away all records with missing data? No. You have to really understand the domain to know what the missing data means, because in some cases, missing data in itself is useful signal you can use for modeling. But in many cases, missing data was just down to carelessness, because at the point of data entry, maybe they didn't enter all the required variables. So you have to understand your data and spend the time to prepare it for modeling. This is not pretty. It's not fun. But actually, it's one of the most critical things you will do in your modeling process. Because if you don't get the data right, everything else is a waste of time. And typically, we also find, even at Microsoft, that this is where you spend the bulk of your time when you build predictive models. We typically spend anything up to 65% of your time on the data collection and preparation phase. Now, once you get the data in the right shape, you're ready to play. You get into step 3, which is the fun part. That's where you actually build the models. I'll say more about that in the next slide. And when you're done building the models, you get your final output. Then you deploy it in a way that makes sense for your business. But the story doesn't end there. Because with these statistical models, regardless of the algorithms you use, they are rarely brittle. Once you deploy it, your population, your customer demographic changes even slightly over time. And so you have to monitor your model in production to make sure that your hypothesis is still true. You have to make sure that it's still performing on your new data set in the way that you expect it when you built it in the first place. And so monitoring of your modeling is absolutely critical during production. Because when you monitor your models, at some point you realize that there's a significant deviation between the way it's performing now and the way it was meant to perform. And that's a good trigger to start and to basically go back to step 1 and build a new model. So that's the generic process. Let's talk about the specific case of how you apply this model or this process to build a real predictive model in practice. And the example I have here is credit scorecards. Hands up who knows their FICO score. Wow. We all have FICO scores. I don't know mine. I hope it's good. But all of our FICO scores actually come from a credit scorecard. And that credit scorecard in itself is a predictive model, right? So let's just go quickly through how we build it. I won't go through every single line item here. I'll just talk about the highlights. You can follow up because these slides will be available to you afterwards. But it starts, as I said, it starts and ends with the business problem. What business problem are we trying to solve? In this case, for predictive scorecards, the lender, whether it's a bank or a credit card company, wants to know one key question. Before I issue this loan to Val, will Val pay up this money or not? What is the chances that Val will default on this loan? That's the most critical question they have to answer before anything else. And for that, they need a predictive scorecard. So they move into step 2, where they collect data. And you collect data from multiple sources, from the bank, from third-party agencies like credit bureaus, etc. And they have to spend a lot of time cleansing this data and preparing it for modeling. Typically, most of the big banks will have an army of risk analysts, and most of those guys are statisticians. These are the guys who invest the time to understand the data. They have to understand it thoroughly, right? Deal with missing variables, deal with outliers, because you don't want outliers in your model. It'll skew it. And once you understand, you clean up the data, you have to also deal with things like covariancy. You don't want to throw in too many variables that are highly correlated into the model, right? You have to deal with things like continuous variables, because depending on what algorithm you use, you may not need a continuous variable. Take logistic regression. Logistic regression is great. In fact, it's a de facto algorithm used for scorecards. But logistic regression doesn't like continuous variables. So if one of your variables is income, which is a very powerful variable, you have to take the continuous variable and break it up into buckets. You basically create categorical variables. So you have to invest the time to do this cleansing and pre-processing to really get a meaningful model. And once you get the data in the right shape, life is good. You go on to build the model using one of the many predictive algorithms out there. For credit scoring, logistic regression is the de facto standard. Most organizations use this to actually build the scorecards. And by the way, depending on which algorithm you use, in most cases you build your model in a two-step process: training and testing. You basically take about 70% of your data, you use that for training. And once the model is ready, if you feel it's accurate enough and valid, you then test it on the holdout sample. You could even use multiple data sets to do validation. That's actually more robust. If you use multiple data sets, then you avoid overfitting. And the interesting thing is, after all of this long process, the final model you get out of this is nothing but a function, right? The credit scorecard is actually a mathematical function that says the FICO score is some constant plus weight 1 times variable 1 plus weight 2 times variable 2, etc. It's nothing but a formula, right? So once you finish modeling, you have that formula. Yes, you spend the time to document it, but you hand it over to the guys who actually deploy it in operations. And as I said earlier, monitoring is a critical part of it, because no model will maintain its fidelity forever, right? It's just the nature of the business, because data changes over time. Typically, by the time you deploy your credit scorecard in production, it's already starting to degrade. Because what you find, based on my prior experience at Equifax, is by the time you deploy in production, the data itself is at least 6 months old, right? Because you took about 6 months to collect the data, prepare it, and go through everything before actually putting the model in production. And while in production, your customer base changes for many reasons. Policy rules, for instance, right? If the bank passes a new policy, maybe you start excluding certain classes of customers. 2, new campaigns. With new campaigns, and whether it's marketing or sales campaigns, you may start targeting a new demographic of customers who were not in your initial set, right? You could, maybe marketing finds, young college students would be a very good prospect. So let's start recruiting. They run a campaign. They bring in a whole bunch of eager beavers from college. The problem is those guys were not, that demographic was not in your initial training set. So your model will not be very good. It will not predict accurately on that demographic, which is why you have to constantly model it in production to make sure that it's still maintaining its fidelity. And at some point, when you find that your model is starting to degrade significantly, that's the trigger to go off and build a new model. Okay? So we've just introduced predictive analysis, talked about the 5-step process you would use. Now let's see what Microsoft actually offers, what tools we offer to help you with predictive analysis. Some of you may be surprised to know that we have shipped predictive analytics tools as part of SQL Server for many years. We actually ship these data mining tools in 2 places. First, SQL Server Analysis Services, and second, in Excel. So let's see what's in each one, and I'll show you more in the demo in a minute. So in Analysis Services, we have a rich library of pretty powerful data mining tools, the sort of tools you can use to do diagnostic or even predictive analysis. But the great thing about the SSAS solution is that it's very flexible and programmable, because we actually have a programming language around it called DMX. So you can use that program, you can basically automate the training and testing, especially the testing phase, right? Once you have the right data, you build your model. In a program, you can actually call that formula you spat out of the model. So you can use DMX to embed data mining into your app. The second one is Office, where we actually have a data mining add-in for Excel. Actually, in this case, Excel is nothing but a client, because you still use all of those rich data mining tools, like the neural networks and decision trees from analysis services, but this time you're using it in Excel, and I'll actually show you in the demo what they look like. But the beauty, and this is one of the main reasons we shipped it in Excel, is to really democratize predictive analytics, to take it to business analysts who live and breathe Excel, so that they can build these customer segmentation models, they can build predictive analytics models without necessarily understanding the deep algorithms we have in the box. So it's very easy to use, as you'll see in a minute. Okay, I have talked the talk so far. Now let me show you how we walk the walk with our tools. And for that, I want to show you how we applied our own predictive analytics tools to solve two key problems at Microsoft. And this is a real case, by the way. I'm not allowed to mention the specific product, but what I can tell you is that these problems are actually, and we're actually applying this in one of our incubation business, right? Because at Microsoft, when you start up a new idea, Microsoft is very interesting because it's a large company, but we also have a place to run startup businesses. It's actually, that's called our incubation business. So when we start up a new idea, we typically put it in incubation and build the business like a startup until it gets big enough to graduate into a mainstream business. So as you can imagine, within our incubation business, there's a lot of unknowns, right? You are in startup mode. So there's a lot you don't understand about the market. You have to do a lot of testing. So we use predictive analytics to solve two key problems for the incubation business. The first one is, who are the best customers for this particular product? Which customers do we target? Because you can't carpet bomb the whole market, right? It's too expensive and ineffective. Then the second problem we solved was, we did win-loss analysis for this business, because they knew that, when they look at their customer base, there's a set of customers who on paper look like good prospects. These are guys who they think will actually buy the product, but in the end, they don't actually buy. So the question is, why? Why don't they buy when they actually look like good prospects? So let me show you how we actually solved both of these problems. So with the first one, we actually built a customer targeting model. It's basically a predictive model we built to predict which customers are most likely to buy this particular product. And for that, we used three key algorithms from our data mining tools. We used decision trees, neural networks, and naive Bayes. And as I mentioned earlier, the data is critical. In this case, we had data from two sources, both internal and external, right? Internally, we pulled data from our sales data warehouses, right? Typical sales data, you know the customer, you know exactly what they bought and how much. But for external data, we pulled data from Dun & Bradstreet, and then we also had country-level data from an external source. Then we applied our data mining tools in SSAS and Excel. And this is just a cleaned-up version of the decision tree. I don't expect you to actually read everything. I'll show you more in detail in the tool itself. But the decision tree basically mines the data and tries to find the variables that are most influential in predicting the propensity to buy. And in this case, the most predictive variables were our partners, and that's why Microsoft love our partners. So this is a great shout out to all the partners in the room. But it's for real. I mean, this model, it's a mathematical model that actually tells us what we knew. It's a confirmatory model that our partners are critical. Basically, in deals where we had partners, we're more likely to win. Second one is competitors, right? Depending on which competitor is present, you're more or less likely to win. The license type was also very critical. And then you'll notice that we also have a set of external variables that we pulled from third-party sources that are actually highly predictive. Things like the country GDP, their education spending, R&D spending, etc. And this is one of the real beauties of big data. Big data is not only about large petabytes of data sets, it's also about integrating unstructured data into your model. It's also about mashing up your own data with data from outside of your organization. And we actually see it loud and clear in this case. So this is a typical lift chart. Yes, sir. Hi, Jeff.
Yeah, hi. On the previous slide, what are those little green bars at the bottom? Are those the percentage of things that happen?
Yes, that's a good question. Yeah, that's your probability to buy. So the longer the green bar, I think that in this case, the longer the green bar, the less likely you are to buy. But I'll show you more in the tool itself. Yes. So all is your initial population. You start with the whole data set, and then through training, the algorithm will find the top variable that's the most predictive. And in this case, it's partner involvement. So based on that variable, it will basically break the data into two sets, right? So based on the answer to the partner subsegment, part of the data will fall in bucket 1 in the top branch. The other half will fall in the bottom branch. And then it continues mining the model. And for the top branch, you find that competitor number 4. I'm not allowed to mention who is competitor number 4. But competitor number 4 is the most influential. And so you do that, you run that process iteratively until you get the full tree. Unfortunately, we had to obfuscate the data because this is real. It's live data based on a real business, so I'm not allowed to share the gaudy details. Does that answer your question, Jeff? Cool. And so we also have in the box some pretty powerful tools you can use to measure the effectiveness of your model, just to make sure you're not just messing around. And one of those tools is what we call the lift chart. It's also called the Gini curve. The green line on the diagonal is where you'll be if you did this. If all you did was random guesses, then your predictive model will be on the diagonal line in the green. So if your model is any use, it has to have a lift on top of the 45-degree line. And that's why you see the yellow line there, which is the result of a decision tree. I'll show you more in the tool. So that's the first model we built to find the right customers to target, right? It's a purely predictive model that predicts forward based on historical data. The second one was win-loss analysis. So the key question we had here is, why do some customers don't buy, even though on paper they look like good prospects, right? And so to solve this problem, we did segmentation. We basically used the same data set, but this time we used clustering techniques to find real customer segments in that data. Because when you get the customer segments, you can drill down into their profile to really understand what's going on. And that will tell you, in many cases, why your customers behave in a certain way. Okay? And this is an example of what the clustering solution would look like. The colors show your likelihood of buying. So the blue ones are customers who are more likely to buy. And then the lines show two things. if you have a line between any two clusters, it means those two clusters are similar, right? They're two distinct clusters, but they're similar. And then the intensity of the line shows you the degree of similarity. So the lines with the thick lines basically show that those two clusters are very, very close to each other. For example, you have a thick line between cluster 3 and cluster 8, which shows that those two clusters are very similar. And so with this type of analysis, we actually started shedding light on why some of our customers were not buying when in principle they were supposed to. If you look at cluster 3 and 4, that's a very good case in point, because those two clusters are very, very similar, as you can see from the thick line, right? However, the guys in cluster 3 were more likely to buy. 51% of customers in cluster 3 actually bought the product, whereas only 16% of customers in cluster 4 actually bought, right? But these two clusters are very similar. And so the tool also has a feature you can use to do side-by-side comparison of those two clusters. And then you actually see very easily why customers are behaving in the way they do, right? We'll see more about this in the tool in a minute. And so with that, I want to show you how these tools actually work. And let's start very quickly with the first tool, which is SQL Server Data Tools, right? This is the old BI Developer Studio. So this is the tool you typically use to build your SSAS cube. You can also use the same tool to do data mining. And so what we're looking at here is one of those decision trees we built in SQL Server Analysis Services, right? This is the real tree. Again, the color, we start here. The color shows your likelihood to buy. So the darker colors are for customers who bought, and the lighter colors are customers who didn't buy. So in this case, for instance, at the first level, the most powerful variable is this one here, partner subsegment. It says if the partner subsegment equals a certain type, then in this case, they're less likely to buy, whereas down here, they're more likely to buy. And then the next, for this bottom branch, the next level is your licensing program. At the next period, we have either the subsidiary name or when the account was created, etc. Let me show you how you would actually build it in Excel. So here we are. In Excel, once you install, so we have this data mining tool that you can install yourself. It's a free add-in for Excel. In fact, it's been refreshed now to work in Excel 2013. Once you install it, you'll get two new ribbons. The first one is the data mining ribbon, which shows you the range of tools we expose, the data mining tools that we expose in Excel. The first three tools here are for data cleansing and preparation. We also have a range of rich data mining tools here, and I'll show you more in the box. And then this last set are the tools you use to test the predictive power of your model. So the first one is the one I showed you, the accuracy chart, also called the lift chart or the Gini curve. You can actually test the profitability of your model as you go along. So that's the first ribbon. The second ribbon is this one, the table analysis tools. This one only works on a selected table. But it's pretty powerful because it's much simpler than the first set, the data mining tools I showed you. But underneath, we're still using the same machine learning algorithms in analysis services. The only difference is that we really simplify it so that a business analyst can use this to build their own clustering models. They can do some basic data pre-processing. They can even use it to build their own regression models, those credit scorecards very, very easily. They can use it to build a recommendation engine, right? A tool that will say, a model that will say, if this customer buys product A, which other product are they more likely to buy? Okay, so in this case, I will use the data mining tool because it's much more flexible. And the first thing I want to show is how we build want to see how we build this clustering model. So I'll select the data, go next. Here is where you actually split your data into training and testing. You can either do it by percentage or you use a fixed number. In this case, I use a fixed number because I have a limited data set. I only have 14,000 rows. I don't want to hold out 30%. So in this case, I just hold out 1,000 rows for testing. And, there's one more thing. All right. So back here, it's very important. This is where you select the models that go into the variables, that will go into your model. Notice that we have over 70 variables here, right? It looks big, it looks clean, but that's because we've already done a lot of pre-processing outside Excel, right? We started with hundreds of variables from our own sales data warehouse, from Dun & Bradstreet and other external sources. And through pre-processing, we narrowed it down to 70. But still, not all of these 70 will be very predictive. So you have to, first of all, eliminate the obvious ones. Like some of those variables are not very predictive. I'll just go down and take them out. The tool automatically didn't select the competition variables, but I know they're very important, so I'll include all our competitors. I want to take out the revenue CD variables because we found they were not very clean. So I'll go down, just take out some of the obvious ones I know, and then I'll let the tool do the rest of the work. Opportunity ID shouldn't be there. That's just your reference data. Year started was not very predictive either. In fact, it's not very clean. The quality of year started was pretty bad. So I'll just take out a few of the variables I know are not very good, and then we'll be in business. There's one more rogue variable I'm looking for, which is an internally coded variable, which was not very good. Yep, that's a sales cycle. So once you select all your variables, I'll go ahead and break them up into test and train data. And if I click Finish, the tool is now building my customer segmentation model. So in the training phase, it's basically doing data clustering, right, using the Microsoft clustering algorithm in the background. The important thing here is this processing isn't happening in Excel because the actual machine learning algorithms are running in the back end in analysis services, right? Must have missed something there because it only came up with 2 clusters. I'm sure I missed a variable there. But if I don't want to go back in the interest of time, but if it came up with all my variables, you see it would actually show all the clusters, and it shows a link between them. Then you can go in and see, do a side-by-side comparison of any 2 clusters. So in this case, I'm comparing cluster 1 with cluster 2, right? You can see why they are different. You can actually see the actual variables that drive customers to go into cluster 1 or cluster 2. So that's the first one. Do we have time for a second model?
Sure.
Okay, thank you. Saptak says I can go. So the second model I want to build quickly is one of the predictive ones, the ones that target the most likely customer to buy our product. And to do that, you can use one of 2 tools. We have an estimate tool here, and there's a classify tool. The only difference between them is the estimate tool will help you predict a continuous variable. If you're trying to predict, for instance, someone's income, then you would use the estimate tool. But if you're trying to predict a categorical variable, you need to use a classify tool. And to use that tool, I'll just follow next, select my, my data. Then we want to do 2 things. First, you have to define what variable you're trying to predict in the first place. And in this case, it's this variable, whether we sold the product or not. Second, you select which algorithm you want to use from our data mining tools. Because we have several. You can either use the decision tree, which we did in this case, or you can use any of these other ones. Logistic regression, we have naive Bayes, we have neural networks. It's a classic multi-layer perceptron. It also shows you, once you select your model, it shows you the parameters, the default parameters of the model. And you can go ahead and actually add more parameters if you want to. But I'll just select the default parameters and move on. So again, I need to select the most important variables that will go into my model, because not all of them, I know, from testing that not all of them are predictive. So let's just quickly go through. I'll add the competitive variables because I know they're actually predictive. PC count is not very reliable. It's important, but unfortunately not reliable. Take out these few ones. The company age was good, but it had some serious errors there, so I'll take it out as well. Same thing with year started. So just a few more variables, and then we will be in business. I think all of the other, apart from this one, all of the other variables are good to go. So we do the same thing again. We need to break the data into two, a training data, and then I'll hold out 100 records for testing. And once we do that, the data mining tool will go ahead and actually build the model. So it's actually building the model live in SQL Server Analysis Services. So we're now in the training phase where it basically mines the model over several iterations, right? During the training phase, you're basically teaching the algorithm to learn from the data, almost like you teach a child to read, right? And then when you finish, you do the testing phase. So now it's done, and if I just move this thing out, adjust the view so you can see the full tree. So that's the full decision tree. So as Jeff asked earlier, and Jeff, you had a question.
Yeah, you keep on saying analysis services. I thought you could point this to PDW. Can you or can't you? We need analysis services in the way.
No, you do need analysis services because that's where the actual data mining algorithms live. You can use PDW, but in this case, PDW will not do the data mining. These decision trees and the neural networks don't live there, right? In this case, you would really use PDW as a source, a data source. From here, I could point to PDW, pull data from there, and then mine it. But when you run the algorithm, it's actually using the machine learning algorithms from SSAS. So basically, it found, earlier I said the most important variables are the partner subsegment, and you see it here, the competitor type. In this case, competitor number 4 is very important. I wish I could share who's competitor number 4, but I'm not at liberty to. Then the license type is also very important. As you know, we offer a long menu of licenses, right? For this particular product, it turns out there's one license type that's a big driver of the customer's propensity to buy. And, I could go on forever. If you hover over it, you'll see how many customers actually bought for each branch. So up here, up to 1,000, almost 1,200 customers out of 5,600 bought. But down here, we had even more, almost 3,500 out of 7,000 customers bought. So you can play around with it and find out more. But the other view I want to show you is this. This is a dependency diagram that shows you which variables are most predictive, right? And you can adjust the intensity, the strength of the relationship by using this slider here. As I slide down, it only draws lines between the strongest variables, right? So if we just leave it there, you'll see again that the partner is critical, and that's why Microsoft loves our partners, right? So the partner is very important. This competitor is important. See another partner variable again. And then there's also the license program and the subsidiary name. So you could play around with this thing all day, but in the interest of time, I'd like to stop here and hand over to my friend Saptak. Saptak?
Thank you so much, Val.
Okay.
Okay. So again, thank you, Val. And that was the most important part of the show. You kind of survived it, and now you're data miners. Now, once you have had a chance to play with your data, build a model, and still see a path ahead, actually see some value out of this exercise. In today's day and age, oftentimes we have businesses where we collect a lot of data. One such example, or very common example, is, say, businesses like Netflix or businesses like Amazon, right? So, for example, Amazon has clickstream data. As you go around buying stuff, looking around different items, it's collecting every click of yours and everybody else. And they have this data now. How can they use this data to predict or to do recommendation around what are the other things you might be interested in? Similarly, Netflix actually very famously did a $1 million challenge where they said, if you can improve the prediction of which movies that users are more likely to select and what their ratings will be by about 10%, will give you $1 million. And it's a very, very famous case study. So just that much improvement in terms of predictability has a huge, huge return. Typically, it has been seen, especially around, say, shopping carts and so on. If you have a good recommendation engine and if you recommend the right kind of products, you typically upsell by almost about 15%. Now, especially if you are collecting data from millions of users or even around machines, you typically your data set is so large you can't do this on a single machine. That's not to say 90% of businesses can probably meet all their data mining and predictive analytic needs using Excel, and if not Excel, with SQL Server Analysis Services. And only about 10% of very large businesses who collect a lot of data will need this kind of distributed infrastructure. So at this point, I'm going to first talk about the distributed infrastructure that we recently announced on top of Azure. The service is called Windows Azure HD Insight Service. It's quite a mouthful, but it's basically Hadoop. How many of you are familiar with Hadoop? Wow.
Wow, everyone. That's great.
So it's the good news for those who are familiar with Hadoop or are already using Hadoop. This is 100% Apache Hadoop. So all your experiences around Hadoop continue to be relevant. Now, for those people who didn't raise their hand, there's even a better news. The better news is we have made Hadoop incredibly easy on top of Azure, and I'm just going to show that in my demo. Okay. So this is Windows Azure portal. If you sign in, if you have a MSDN subscription, you, by the way, have free Azure hours, which you can use to do all kinds of things, including HD Insight. So once I log in, I see all these services that I can use. Now, I'm going to focus on two specific services today. One is the HD Insight service, which I talked about. So if you go to Data Service, you'll see the HD Insight service. Now, it's in preview, so yours might be kind of grayed out, and then there's if you click on it, there's a thing called Request Preview or something like that. You have to fill up a short form, and then you get access to it. Now, the cool thing is that it is associated with the Azure storage. So what does that mean? So we have had Azure Blob Storage, as it's commonly known, as an unstructured data store on top of Azure for quite a few years now. And what Windows HD Insight Service does is it can mount Azure Blob Storage as its storage and process the data there. Now, you might not think it's a big deal, but it is for several reasons. Let me explain why. First of all, many of our customers over the years have collected a lot of data in the Azure Blob Store. Now they can do analytics on that data using Hadoop very, very simply, and I'm going to show you how. Secondly, when you spin up a distributed infrastructure, it basically means you are spinning up many, many VMs because you want to collapse the clock time required to process all that data. Now, of course, spinning up a lot of infrastructure means, you'll have to pay for that infrastructure. But you might not need it for an extended period of time. You might just need it for the time you do the analysis. So you spin up the infrastructure, you do the analysis, data mining, whatever you want to do. You store the results back in Azure Blob Storage, you spin it down. And you can do it all through the API that we have for HD Insight Service. Now, having said that, let me show you first of all, the storage that I'm going to use. So I'm going to use this blob storage called Saptak Demo. And I'm going to copy this key. And I'm going to, the reason I'm copying this key will become apparent soon. Then we have the HD Insight service. I have two clusters running, one 8-node and one 4-node in this case. This is the 4-node cluster. And I'm going to connect to it. So if I click on connect, it's going to ask me to download a .rdp file. .rdp is basically a remote desktop connection. Now, I'm already logged in. I hope I'm not logged out at this point. Okay. Yeah, there you go. So let me, okay. So this is the head node or the name node of my HD Insight cluster. So basically, we have if you had said a new cluster, in under 10 minutes, we can spin up a distributed infrastructure fully configured for data processing in under 10 minutes. And once you log in, it's just Hadoop, so all your existing application work and so on. Now, you see on the screen, I have a thing called Mahout. Now, let me talk about Mahout, because this is the relevant part for the data mining part of it. Now, Hadoop's computation paradigm is called MapReduce. Right? Now, everything that you want to do on Hadoop will have to be today expressed as MapReduce. So what does MapReduce do? In like 2 sentences, let me describe what MapReduce is. MapReduce, as the name suggests, has 2 main components, mappers and reducers. So what does mappers do? You have a distributed storage. So all your data is sharded onto many, many disk drives, physical disk drives which might or might not be in the same machine. Now, once you launch a set of mappers, they parallelly start reading all these different shards of the data set that you want to analyze parallelly at the same time. And once it starts reading that, it as key value pairs, it does some basic transformation and sends it back or emits it out as transformed key-value pairs. And then in the reducer side, what you do is you shuffle all these key-value pairs and group it by keys, and each reducer gets a group of a particular key, all the key-value pairs with the same key, and then they can do the aggregation. So it's a very simplistic computation model. Now, once you are trying to do a complex computation paradigm, even like something like join, it's very hard to do it with MapReduce. MapReduce is extremely good for what we call embarrassingly parallel problems. Euphemistically, we sometimes call it delightfully parallel problems, right? So, for example, Monte Carlo simulation that Val was talking about, where you are basically going through a set of parameters and basically trying the same algorithm with different parameter. You are doing a parameter sweep. Those kind of algorithms are embarrassingly or delightfully parallel. Now, if you want to do anything more complex than that, then basically it results in multi-stage MapReduce. So there needs to be multiple MapReduce jobs which needs to be chained to be achieved, for that to be achieved. And that dramatically reduces the parallelization and thereby the efficiency of your distributed infrastructure. So the reason I'm spending so much time on this is that not every data mining algorithm is suitable for our distributed computation paradigm like MapReduce. So Mahout is a library which started as part of the Lucene project, Apache Lucene project. If you know about Lucene, it's basically a search engine project. And they carved out a small portion of the Lucene project and spun it off as the Mahout set of libraries. The Mahout set of libraries provides a bunch of data mining algorithms, but the three most mature algorithms are clustering, classification, and collaborative filtering. Now, it started with actually the collaborative filtering, because the collaborative filtering was used to develop a recommendation engine for many large internet powerhouses. They actually use that collaborative filtering algorithm. Now, with that, let me talk about a problem. Let me actually show the demo of something running, right? So the situation is that we have this data set. It's from hosted on Columbia University. It's called the Million Song Dataset. So they have basically collected user ratings on songs from Last.fm, Music Match, and a bunch of other places where you listen to streaming online music, and people rate those songs between 1 to 5 stars. So they have collected that, and they have opened it as a data set which you can play with. It's actually, they released it as part of a competition, actually. So essentially, the data set contains 3 things. First, the user, obviously. If you, I don't know if it's too small or whatever, but I don't think the details are that important, just the concept. So the first part is a big GUID, which is the user. The second part is the song that they listen to. And the third part is the, how many times they have listened to without skipping it. So that gives a sense as to, how much they like it. Now, the Mahout library expects data to be inputted in a certain format because they can't be too general, right? So that's where data preparation becomes so important. What we did was we actually ran a Hadoop job. We took that basic library, and then we cleaned it up. We cleaned it up in a way, or I shouldn't say cleaned it up. We basically transformed it to a way where Mahout libraries can understand it. So let me show you the input data set very quickly. So this is my Hadoop file system, basically. It looks like a Unix file system for obvious reasons. Now, this is different from the NTFS file system locally on that machine. It's an abstraction. It's an abstract file system which is spanning all the machines of the cluster. So this is where my input files are. Yeah, I'm running out of time. Believe me, I'll be done in 5 minutes. Let me quickly show you the file. So Mahout expects that all inputs will be integers. So basically, the user, the first one is the user, the second one is the song identity, and then the play count. That's the third column. And that I'm going to use to run a Mahout job here. So this is the Mahout job. Now this is going to read up that file or pieces of that file on all those machines and start processing it. Now, as I start processing it, so let me change this to output 2 so that it's in a different folder. You'll see that it's actually running multiple MapReduce jobs. It's basically doing a very simple similarity co-occurrence. You can do all kinds of similarity signs, similarity, Euclidean distance. There are a bunch of other algorithms which you can play with, but let it do what it is doing. But in the meantime, what I can do is, once this is done, the result is 3 things. The user, and then a list of songs that he's most likely to, that's recommended for him, and the rating that he would give. That's the output. So let me show you how the output looks like in the meantime. So I'm going to come back to the local machine, and I'm going to fire up Excel at this point while the job is running, because I've run this job before, so there's already a result. So I'm going to use something called a data explorer. How many of you have seen the demo in the keynote that Aaron did? Isn't it cool? Yeah. So I'm going to connect to my Azure HD Insight, where my job has ran before and currently running as well. So it's asking for the account key. Remember, I copied that big GUID from, only if I can paste it here. There you go. So now it's going across the interwebs and grabbing me all the file set sitting on my the storage associated with my cluster. Now let me grab the file, output file from here. So So this is my file. This is what I get. I know it's too small to read, but it's like first, Control 1. So this is what it looks like. The first part is the number. which is the user, and then a bunch of song IDs and a rating that he'd give for that song. Now, once it's in Data Explorer, I can start cleaning it up and transforming it in a form that I can use in other data models. Basically, I can even make this a source from a Power Pivot model or a tabular cube for visualization.
Right.
So that in short is the demo. For example, if I want to split it, what I would do is by delimiter, in this case it's space, or it's actually, the square bracket, starting square bracket. Immediately, I've got two columns. One is the user, one is the list. And I can keep doing this, and it's actually creating a script on the sample of the data, and which I can, once I'm done, I can apply on all the data. Now, with that, let me go back to the deck and finish up. Now, a few things to watch out for when you are doing predictive analytics on Excel analysis services or on Hadoop, irrespective. First of all is the sample bias. What that means is that if you've got a wrong or skewed sample, irrespective of how much work you put into it, your model is going to be, for a lack of better word, $HIT, right? So that's very important. So especially if you get an ordered sample, first thing you do is randomize it. Because if you take it from the first portion of the thing, the head of it or the tail of it, your sample is skewed. That's one. The second aspect is if the sample size is small. Let me do a quick quiz of coming up with a model. Let's say you have three numbers, 0, 1, 2. What could be a predictive model which predicts the next number? Maybe it's a linear model. The 0, 1, 2, maybe the next number is 2, right? 0, 1, 2, or 3, right? But it may not be true because the sample size is too small. It could be a Fibonacci, series. That could be your model. So there's no way, given that sample, that you can come up with the model. That's one. The next thing is overfitting the model. So you got a bunch of data, and you have overanalyzed it to make your model, predict every point 100% correctly in that sample. Now, as soon as you apply the model to what we call outside data, that means the data that while you created the model you were unaware of or you were blind to, your model fails because you have made it so specialized to that sample that you are working on that it's lost all generality, any kind of predictive capability which could be valuable for a larger data set. And thirdly, it's about the worst sin is poor interpretation. Means we know all of us have confirmation bias. We subscribe to certain political views and we try to get or prove with different hypotheses our political views, for example. Let's say I have a view, I'm a dog person. All cats are evil, right? So I'll try to look for all images with cats looking evil on the internet to prove that cats are evil, right? So, yeah, so I think we are just over time. Lastly, I want to say that please fill in the survey. And we have done some modeling, and we have found out the likelihood of winning that Xbox is very highly correlated with your score of this session. I'm just kidding. I'm just kidding.
If you want to win the Xbox, if you want to win that Xbox, you know what to do. Score, rate us highly. No, sorry guys, sorry for
I'm kidding.
running a bit over time. Yeah.
Thank you.
So we will have to, we'll wait for you guys by the side of the room. If you have any questions, we'll be here for the next hour if you want. Thank you very much for your time.
Thank you.
Thanks, Saptak. Thanks. Hi, how are you? Hi, was that useful?